Hi everybody, welcome back to the channel. Today we are looking at section 2.4, the first day of 2 days of factoring polynomial functions in order to get them graphed. Now behind me, we've got a function here. F of x is equal to x to the third plus 2x squared minus 4x minus 8. And we're going to be asked to factor this in order to get this done. Okay, that's really the only difference that you're going to see from what we did in section 2.2 to section 2.4 is that we're going to have to deal with functions that are either partially factored or not factored at all. So you might be thinking, just get it factored and we're good? Pretty much, but there are some nice things that you get out of it as well from the unfactored form. So I'm going to make a suggestion here. As we start doing these problems, get the problem factored first. Then we'll take a look at how we get that end behavior, get our y-intercept, get our x-intercepts, get our zeros. We'll do all that same stuff, but we get a couple of things that are a little bit faster from the unfactored form. Let's hit it. Here we go. So in this particular case, all of your problems for section 2.4 day 1 will be problems that you can factor by normal methods. So in this particular case, we would have to look at this and say, all right, we have 4 terms, factor by grouping. So I'm going to go ahead and do that. So I'm going to take a look at x to the third plus 2x squared and group those. Negative 4x minus 8. I'm going to group those. Again, making sure don't make the common error here. Group that negative here. That's important. And now from here, just factor your GCF. So out of the first group, we should recognize x squared. This will give us x plus 2. Out of the second group, we'll factor a negative 4, which will then give us another x plus 2. Now we've got a common group, x plus 2, x squared minus 4. This is hopefully screaming at us. In its fully factored form, x plus 2, x plus 2, and x minus 2. Now, what we'll do with this, you'll notice that what ended up being generated here were 2 quantities of x plus 2. So our function, in its final factored form, we can write as x plus 2 the quantity squared times x minus 2. So you will have some factoring, multiple steps to that, where you're going to probably generate a couple of factors that then create your multiplicity for your problems as you move forward. So from here, now we start doing the same thing we did before. We're going to go ahead and find our end behavior. We're going to find our x-intercepts or our zeros. We're going to find our y-intercept. Get this. 2 of those in a fully unfactored form polynomial function, you can get immediately. Nothing has to be done. Now, let's make a comparison here. So my factored form of the function we have is x plus 2 the quantity squared times x minus 2. Now, if I start doing the end behavior and I start taking a look at f of x, you really have 2 different options to figure this out. Or maybe a better way to put it is you have one way you can do it and another way to verify it. Now, if I did my processing from what we worked with section 2.2, we would look at this and say, okay, same argument, the $1 million argument, adding $2 to $1 million or taking $2 away from $1 million, really not a big deal, okay? So we'd recognize we could say x squared times x, and we would say that our approximation is x to the third. Now, make a comparison. Look at our approximation and look at the unfactored function. Look at the first term. of the unfactored function written in descending order. You should recognize something. Essentially, what we're doing from a factored form in this approximation is coming up with the first term that would exist in the unfactored form, the first term with the highest degree. So if you think about the unfactored form here, the most powerful term as x gets really, really large will be the term that cubes my value. Okay, thinking about it for a moment. If I take 10 to the third power, I have 1,000. If I take 10 to the second power, I only have 100. Or 10 to the first power, which is 10. The largest or the most powerful term that creates the biggest impact as x gets really, really large is going to be your first term or the highest degree term in the unfactored function. So we have two options here. The quick way, look at the unfactored. There's your degree. It does show up in the approximation, so we can use it whichever way that we feel more comfortable with. But we should recognize from here, third power. By now, we should recognize that this will have n behavior that will be lower left and upper right. From here, let's keep moving. Let's go get the zeros. Now again, we'll do this through a direct inspection. Okay, so our direct inspection would say we're going to get a 0 at x equals -2 with even multiplicity, and at +2 with odd multiplicity. So I can plot those. So -2, even multiplicity, +2, odd multiplicity, and finally get the y-intercept. Now, here again, we have two different options in order to find it. If I did it by the methods that we saw in section 2.2, we would be essentially finding f of 0, which means that in the factored form, the x's are going to 0, leaving us constant factors with multiplicity. So we could argue 2 squared times -2. And we can go ahead and calculate 4 times -2 is -8. Look back at your original unfactored function. Do you notice there's a -8? The last term. So notice in an unfactored form, I actually get 2 of my aspects, or 2 of the main characteristics I need to be looking at in order to graph the function. So I can go ahead, again, we don't want to make a whole bunch of extra increments. I'm just going to come down here, label it 0, -8. And I have my critical points. But here's the big catch to this, everybody. In a completely unfactored form, my first term gives me the n behavior. Okay? So the first term, I get my n behavior. All right? The last term, or the constant term, is the y-intercept. So really what this particular section is going to be about is being able to get our function factored and finding the zeros with their multiplicity. Okay? So we get 2 quick things in a completely unfactored. Now we will have some problems where it's partially factored because we haven't gotten to methods yet that deal with factoring something that doesn't involve factoring by grouping or a difference of squares or a difference or sum of perfect cubes. That's what we leave section 2.4 day 2 to deal with. So as we continue on this problem, we've got all of our pieces. We got our end behavior. We got our zeros. We've got our y-intercept. Again, keeping in mind that that's an ordered pair. If we've done all that correctly, our graph should fit. Let's see. I'm starting lower left. If I start to just mentally trace, I have to come up. I've got to hit an even intercept. Even intercept is going to bounce off. It's going to come down, go through the y-intercept, and in this case, it would bottom out at that 0, -8 because the y-intercept is evenly spaced left to right between these two zeros, or the two x-intercepts. So we come through, we head up, odd intercept lets us go through, and notice that it matches what we anticipated for our end behavior. So what we should find, everybody, is that if we're doing all of the information, all that analysis correctly, our graph will fit. If the graph doesn't fit, we've either made a mistake on how we labeled something on the graph, or we made a mistake in our analysis somewhere. The nice thing is you can always find the mistake. Okay? So there's a few things to consider. If my degree is 3 here, that means I can have at most 3 zeros where I'm crossing the x-axis. At most 3 zeros. Now, reason why we can have less is because of multiplicity. But again, if you consider it, 2 factors that are x plus 2, a single factor of x minus 2, 3 factors. Okay? So as we move forward, where we will spend the majority of our time now is going to be dealing with the factoring aspect of things. Because again, a lot of times we're going to get the beginning and the end behavior, y-intercept, relatively quickly. Let's take a look at the next example. Now, I'm going to challenge you here after seeing this, and we take a look at function g here, to actually pause the video and do the problem and see if you can get down to the same result following what you had just seen. Okay? So we're going to be looking at function g of x